Hello, I'm Amir, and I'm going to present LIFT, Latent Implicit Functions for Task and Data-Agnostic Encoding. It's a work from University of Toronto, Vector Institute, and UHN. So first, I'm going to start with the table of contents. First, I'm going to give a quick overview of what is implicit neural representations. Then I'm going to talk about functa or functional data. And at the end, I'm going to present our work, which is called LIFT. So first of all, what is implicit neural representation? So basically, the world around us is not discrete, and traditionally, we choose to represent real-world signals, such as images or sound, in a discrete manner. It means that, for example, if we have an input image, we have pixel values, or if we have shapes, we have point clouds, or if we have audio, we have samples of sound wave. But discrete representations have two main drawbacks. The first one is that it only contains a discrete amount of information about our signal. And the second one is that the stored discrete data may be very large. So imagine we have a continuous function that can accurately represent our desired signal. But there's a question here. How can we find such a function? So this is what implicit neural representations. The goal of INR is to encode continuous target signal using a neural network. So for example, for an image, we want to have a mapping function that map coordinates, for example, x and y coordinate, to its corresponding RGB values. So imagine we have a neural network which can be a simple MLP that takes x and y coordinate and it predicts the corresponding RGB values of that coordinate. Or you can see it from this animation that, for example, we have a one layer of one MLP with one hidden layer that taken coordinates is gonna reconstruct the U of the logo. But compared to discrete representations, they mostly fail to encode high frequency details. So for example, if you have an input image, if you want to reconstruct it, it mostly generates blurry edges. Or in the point cloud case, for example, in the reconstructed point cloud, it misses coordinates, or the samples of a sound wave in the reconstructed one, it misses some frequencies. So some methods have arrived in order to fix that issue. And basically, if you have an MLP function, you can change three parts of it. So the first one is that you can change the activation function. So the one of the most important work is the siren, that they changed the previously used ReLU activation function to sign activation function. Or you can just change the input. Instead of using implicit coordinates, you can just use the positional encoding of your coordinates. Or for example, you can just change the number of output neurons to specify which part of the image should be reconstructed with what neurons. So here, functa. What is functa actually? So as I said, in the implicit neural representation, the task is that you want to represent one single data point. So you input the coordinate and you get RGB values, for example, for an image. But imagine we want to extend the task for data set. So imagine, for example, you have a 1000 data point. So what can you do actually if you want to, for example, train it for a data set? So that's the idea of the functa. So functa is a functional data, or more precisely, we want to say that implicit neural representations that are to be thought of as data, what it means. So imagine, as I said, you have a 1000 data point. You want to, for example, train 1000 implicit neural representations. So for each data point, you have a one MLP function. And after that, you have, for example, 1000 MLPs, and you can, for example, use the weights in order to do the down-listing task. Like, for example, you can use those weights, for example, for the generation task, like hyperdiffusion, or, for example, you can use those weights for the classification task, whatever the down-listing task is. But the problem is that the weights of those MLPs is high dimensional. So you cannot easily use the weights for your down-listing task. So we want to be more efficient. So that's the solution that the Functa proposed, learning a modulation data. But what is it? So in the Functa, imagine we have an MLP function called f theta. We have an input coordinates, like for example, it is shown in red circle, and we want to predict the RGB values. So right now, it is the same as the single data point representation using implicit neural representation. But here we define a latent vector z that we define it for each data point in the data set. So each data in the data set, we we're gonna map it to a latent z. And then we're gonna pass it by a linear in order to get a shift modulation m. And then we're gonna modulate or condition our MLP function based on that latent z. So if we have an MLP function with a sign activation function, which is called siren, so the idea is that we want to add a shift modulation to this activation function. So as you can see, it is shown in the in red. So the thing is that if you, for example, 1000 data point, instead of having a 1000 INR networks, you can have a 1000 latent vector of Z. So it is more efficient than using, for example, 1000 for example, MLPs for your downstream task. Here you just have a 1000 latent vectors that it is very efficient. It contains all the information from your data point, and you can use those latent vectors for your downstream task. But how can we learn those latencies? So they do it in a meta-learning approach. Like, for example, they first initialized the latent Z, and then they try to update its parameters using 3 steps of stochastic gradient descents, but by having a reconstruction loss. So you input the coordinate, you predict the RGB values, but you're gonna update the parameters of your latent Z. And after that, those 3 steps are done, you're gonna do the outer loop. So here you just fix the parameters, and it is the turn of your MLP function. You just need to update the shared parameters of your MLP function. And here you're gonna update its weights using the Adam optimizer in order to minimize the reconstruction loss. Like, for example, like the reconstruction loss used in the inner loop as well. So we gonna update the parameters of our implicit neural representation in a meta-learning approach. And after that, after we train our network, now, for example, if you have a 1000 data point, you just need to freeze the weights of your MLP and try to do the inner loop, for example, for 3 steps of stochastic gradient descent to get 1000 latent Z. And if you have, for example, test data, you can do the same thing. You can just freeze the weights of your MLP function, do the 3 steps of stochastic gradient descent in order to update your latent Z parameters. And then, for example, uh, now you have a latent vector for each data point that you have in your data set that you can use them for your downstream task. So in Functa, they did it for the two downstream tasks like generative modeling and the classification task. For the generative modeling, one way is that, for example, you can use those latent vectors, for example, just train a DDPM on, or diffusion models on top of the data set of your latent vectors, which we call the Functa set. But the main advantage of Functa is that, for example, in the voxel, for example, grids, as you can see here, if you want to increase the resolution of the or dimension of the rabbit from the 32 on the power of 3 to 64 on the power of 3, you require 8 times more memory. But if you have just a MLP function, you don't need necessarily increase your memory proportionally to based on the increase in your for example, voxel grids that you have here. So basically, you just need to increase the width or the depth of your neural network, which is not proportion to the increase in the size of your increase the dimension of your data point. So as you can, for example, see this example, as you increase the uh, dimension or resolution, you can see here that you in the voxel grid you need more memory, but in the case of Functa, you don't need that. But the functor that they use the global vector in order to do the just use it for your downstream task, they have one key limitation here. So we call the functor a global based methods, which they have a compact representations. The key limitation is that they are relying on global latent vectors that restrict them to capture fine-grained details, which it's gonna reduce their effectiveness in certain downstream tasks. And also it's gonna restrict them if you want to scale our data to high resolution. Like, for example, they are not scalable to high resolution data. And then they have a follow-up work, which is called a spatial functor, which instead of having a one, for example, instead of having a latent vector, they say that, okay, we employ a spatially organized latent codes that gonna also capture localized information. But the problem also exists, like they are also computationally expensive. So what if we want to be more even efficient and also be more effective? So this is a solution that we provided using Leaf framework that we want to unify global, local, and intermediate features in an efficient framework. So this is the basic idea of Leaf. So this is the overview of the Leaf. Imagine that we have a multi-scale latent representation, which is a hierarchy of learnable latents, global, local, and intermediate. We initialize them to capture multi-scale features instead of just representing local information or also the global information. We are defining 3 levels of information. Then these latents are integrated through hierarchical latent modulation, which gonna ensure that we are having a smooth transitions across local patch boundaries by sharing information between regions. It means that if you want to use just local information, the problem is that you are gonna have some inconsistency in the boundary regions. So you're gonna use the global information and also the intermediate information in order to have a more smooth transition across your local patches. And after the hierarchical latent modulation, we are having a shift modulation. We need to provide each local patch its specific shift modulation because we want to define parallel MLPs. So instead of having a very large MLP, we are defining a set of parallel MLPs. So for each local patch, we define its specific MLP that is going to be modulated based on the shift modulation that we are providing from the previous step. So its MLP gonna have its own shift modulation, and we are passing the local coordinates, and then we are predicting the RGB values for each patch simultaneously. So by doing that, we are very fast, we are more effective, and we are more efficient. And for the loss function, we are defining two loss functions. The first one is the reconstruction loss, as the one that Functa used. And the second one is the latent smoothness loss, which we want to encourage as a structural latent space by promoting local consistency among among the learned latent vectors. So in each local patches, we don't want inconsistency between them. We are having some kind of latent smoothness loss in order to encourage a smooth transition between them. And after uh, the definition of the framework, we need to construct a latent data set using the leaf representation. So we train the model using a meta learning approach as the one that the functors used. And but here we're gonna update the parameters of the intermediate, local, and the global vectors or latent vectors uh, in our inner loop. And in our outer loop, we're gonna update the parameters of all of our parallel MLPs. And after if we have, for example, 1,000 data point, we're gonna generate 1,000 uh, spatial latents, which is their size is of the size of the local patches. So if you, for example, patchify your for example, input image, like for example, if you have an input image of 32 by 34 and 32, and if you patchify it by 4, you're gonna have a 8 by 8 local patches. And so after that, we're gonna save those local latent representations for each data point that we have, and then we're gonna perform downstream tasks like the one that Functas used. So we train a DDPM for generative modeling, and also we train vMamba for the classification task. Here it is the qualitative results of 2D and the 3D reconstruction that our approach could actually perform a very good job in order to do the reconstruction task for different types of data. Like for example, we did for the 2D and the 3D. For the 2D, if we scale up our, for example, data set, in that case, even we can reconstruct our data because of the efficiency of our approach. It allows us to scale up the resolution of our data in order to do the, for example, reconstruction task. And in 3D data like ShapeNet, we could also could reconstruct our ground truths very well. And also we tested the interpolation uh, experiment. Like for example, we have a two, for example, images with two different latent representations. We do the interpolation between these two of seeing that are we having a smooth transition between the different latents or not. So here, as you can see here, 2D latent representations show a gradual attribute changes. For example, if you change the attributes of the person or the gender of the person, you can even see the gradual attribute changes. Or for example, for the 3D data, you can see the same thing, that it shows a continuous object shape transformations. And also, this is the results for the generation task for both 2D data and also the 3D data. And this is the quantitative results. Like for example, we tested our approach, like for example, uh, we did the reconstruction and also generation task for the Celeb A dataset of size 64 by 64, and also we scale up our approach to 384 by 384. And as you can see here, we could gain a very high we could significantly surpass the SOTA methods in the reconstruction, and also we did a good job in the generation as well. And also we tested our approach on the ImageNet 100, which is of the size of 256 by 256, in order to show the scalability of our approach. And this is the result for the 3D generation. It is the same like the 2D that we did a very good job in the reconstruction test, that we could significantly surpass the second best method. And also this is the classification results. We train a VMamba on top of our latent representations, and we compare it with the discrete-based methods like Resonance 50 or Resnex, VIT, or Swin. And we also compare our method with functor or spatial functa. As you can see here, we could even surpass ResNet 50 or the discrete-based methods, and in terms of the top one accuracy, even though that those methods, they use more sophisticated augmentations like mix-up or cut mix. And the important thing is that our approach, it's require significantly fewer number of parameters, which it is the same as, for example, 3D data, with which we require significantly fewer number of flops on the learnable parameters, and also for the 2D data as well. Like for example, we require, for example, 54 million number of flops, but the second best approach require about 28 giga number of flops. So our approach is very efficient, and we can say that speed meets quality. So for example, for the Celebi dataset, we could gain a better FPS compared to the second fastest approach by 1.9 times being faster. And also for the ShapeNet, we are being faster by 2.14 times. And also we propose a variant of Lift, which we call it Relift, which we modify our approach based on two factors. The first one is that we change the frequency, we add a frequency scaling factor for the first layer of the siren, which we call it lambda factor. And also we are having a residual connections, and we have proved mathematically in the paper that if you do that, we can increase the convergence rate. And for example, for the reconstruction task on Celeb A 64 by 64, for example, we can get a PSNR of 35 even in 10,000 number of iterations, which is about 68 minutes. So we can reconstruct our data perfectly in just 68 minutes. Now compared with other methods, which they require a very large MLP function, and they require training, for example, for 2 or 3 or more days. And we also test a relief on single image representation tasks, 3D representations for different 3D shapes, and we also tested for the single audio representations that we could see lower reconstruction error compared to the SOTA approach. We show the effectiveness of relief for the super resolution task, single image denoising task, and also single image in painting task. The most important thing about the relief is that you don't need any kind of for example, extra parameters. Without any kind of computational overhead, you can increase the performance of Siren in order to beat all of the SOTA methods that exist in the literature. And thank you for listening.